stuff. Let me check the chat first of all to check whether there is any questions about the stuff that we have just gone through. I don't think there is any questions, so this is good. And actually, I will also take the opportunity to test whether you still hear me, right? And see the slides. Yes, I see Sohan smiling, so that's a positive. Okay, thank you. Thank you. Okay, so let's crack on to part A. Okay, so metric spaces. Okay, so this is really just an abstraction. Metric is just an abstraction of a very intuitive notions that we all have, even without going to mathematics, which is the notion of distance. Okay, so given a non-empty set M, okay, a metric on M is a map we label D that goes from the Cartesian product of M to R. Okay, this is a formal way of saying this map D takes two elements of M and spits out a real number. Okay, and then it satisfies these three conditions. Okay, the first one is this. If you take any 2 points, the distance, the D, say X and Y, D of XY is greater or equals to 0. This is to say that this function D cannot be negative. Okay. Another condition is that D of XY is 0 if and only if X equals Y. Okay. A third condition is this symmetric condition here. So, D of XY is the same as D of YX for all, X and Y in M, right? The distance from London to New York is the same as the distance from New York to London, right? And then you have this thing here, which is the triangular inequality stuff, okay? So these are the conditions for any map, for a map, not any map, to be called a metric on M. They have to satisfy these 4 conditions, okay? And then the pair MD is called a metric space, okay? And whenever the metric, the function D is understood from the context, then there's no need to be writing this pair. We will be doing it because we are working mostly in abstract until we get to the concrete stuff. But yeah, whenever the metric D is understood, we just write M and call it a metric space, okay? And here's another interesting thing. So giving a metric space and a subset of M, a non-empty subset, obviously, we can construct another metric by restricting the map, the original metric, to just to the subset itself, like this. And the claim is that I leave it to you as an exercise, is that this makes this subset also into a metric space. And obviously being a subset of the larger metric space, so it means that this is as obvious as you can guess, is called this a metric subspace, okay? Let me check the chat. I guess this is all, for most of you, this is all like kindergarten stuff. You have seen this before, right? Okay, excellent. So let's see some examples, some toy examples, some interesting examples, okay? So the first one, for any set, any non-empty set, we can, construct this discrete metric. So D of XY equals 1 if X is different than Y, 0 if otherwise, if X equals Y, okay? So this is a discrete metric. This is a bit boring stuff, so yeah, this is useless. But nevertheless, just to showcase how it's actually any set can actually be equipped with a metric structure. Whether it's useful, that's another question. Now, consider M to be Rn. Most of you, I know, coming from analysis and calculus, you know what Rn is. It's a Cartesian product of the reals. So if you have n tuples X, and you have another n tuple Y, we can define Euclidean distance like this. So this is the Euclidean normal Euclidean distance, right? The square root of this sum here. Okay, and the claim is that this thing here is makes this Rn into a metric space. This is indeed called the Euclidean metric space, or the Euclidean space, right? This is the stuff that most of you are already, even if you didn't know it's called Euclidean metric space, you're already used to it. You were already using it. Okay. Another thing is, obviously, you can, when you have a metric space, you can construct. If you have a metric, you can construct other metrics out of the existing metric. So the claim is here. Actually, I've already spoiled it because this is true. So I guess it's just for you to verify that if you have a metric space with a metric D and you have a positive real number alpha, then this guy here, this is also a metric on M. Okay. Now here's a challenge for you, given these metric spaces M1 with M1 D1, M2 D2, blah blah blah. And you construct a metric structure out of the Cartesian product of the respective sets. So this is a challenge for you. Homework for you is to play around with the concept of metric space, giving a metric, go and construct a metric for the Cartesian product. And for those of you, this is where the Hilbert space, just to refresh, to try to force you to go back again to the Hilbert space stuff. Suppose that H is a finite dimensional complex Hilbert space. You guys, I know most of you who have been, joining us since last year, you have gone through the foundation module. We covered we cover finite dimensional Hilbert spaces, so you should know what a Hilbert space is. I'm pretty sure. So the idea is, can you construct a metric on H? Well, the answer I can tell you is yes. And here's a hint I left for you: is use the norm induced by the inner product. Remember that given a Hilbert space and the inner product, you can generate a norm out of it. So therefore, remember, we talk about Hilbert spaces, therefore generate Banach spaces, remember. And also remember that if a Hilbert space is a Banach space, but a Banach space does not necessarily need to generate a Hilbert space, okay? So I'll leave this as an exercise for you. Let me check the chat. Okay. I guess this is also kindergarten for most of you. And now the concept. Sorry, this is very small. I was trying to do the slide just to get this guy here on the thing, so I ended up the thing. I hope you can see. Can you see this slide? Okay, so someone is saying I asked a question. Okay, let me check the question. Amir. Considering we have dealt with norms, what is the relationship to metrics? It's the other way around, actually. Let me start answering. So that's a very good question. So I claim is the other way around. You have, when you have a norm, you can induce a thing. It's true also, if you have metric, you can also induce a norm. But if you have, in this case, I'm asking you, you have a norm, I want you to construct a metric on it. So to answer to your question, yes, there is a relationship between both. You can go both ways for our purposes. Okay, so a very important concept is that of open balls in an existing metric space. So if you have a metric space, MD, for each point in M and a positive real number, you can define this guy here, BR of P, which is essentially the set of all points in M whose distance between from P is less than R, okay? So essentially this guy here, this thing here, you can picture it this way. Here you have the point P, so anything here, the thing that's less than this thing here. So this is essentially this. This is an example in R2 in this case, just for you to see like an intuitive picture. Okay. By the way, I encourage you to draw pictures. Obviously, I cannot, not just the lack of time, but also due to a bit of a laziness, and also to force you to draw stuff, you know, because then it helps you get a better intuition by yourself. Okay. So BR of P is called open ball with centered around point P with radius R. Okay. So obviously, we have this property. I hope you can see this, that you cannot BR of P1 equals BR of P2 if and only if the 2 points are equal. So you cannot have an open ball with the same radius centered at 2 points, at 2 different points. This is actually very interesting. It's already hinting you something. So you can separate points with the open balls. You know, does this hint something that we touched before, Mr. Hausdorff, for instance? Yeah, we'll come back to it. You'll see how this thing play out. So okay, so the concept of open balls is very important, because this is just to give you a heads up. This is what will lead us to deal with the concept, to define the concept of to recover the concept of open sets from the metric space structure. Okay. So this is very important. It's very important you understand what's going on here, because otherwise you will be lost. Okay, so here's a proposition. I hope I got it right. If not, this is a good, actually, if you can find a loophole on this. But I claim this, so I will leave this as a homework challenge. You can ping me on Discord if you are struggling to prove it, but I would advise you to ask someone else to see if they, you know, they managed to solve it, or if they found something, any loophole or something, okay, before you ping me. Okay, so here's the concept of open sets using the metric space structure. Okay, so given a metric space MD, a subset of M is open in respect to the metric D. Okay, so in respect to the metric D, if for any point in U there exists a positive number such that the open ball around with the radius R around P is contained in U. Okay, so that means that for any point in M, this thing is this thing open, this open ball in the thing, is this open? Yeah, I will leave this. I will not answer, because it's very important for you to be able to answer this yourself, so you know exactly what's going on. The same with this other question. So, for example, if M equals the reals and D is the Euclidean metric, the question is, the open interval in the analysis sense, you know, these open intervals are also open in M. Okay. Now another question is that is R itself open? Well, you look at the definition here, and then you will be able to answer this. I really encourage you the thing to go and if you are struggling to see this, to go and try to answer this thing by yourself, because this is really important. And there are other challenges here. This is actually very interesting, this challenge here, because you can see, well, the statement, the question is whether these intervals are not open if M equals R, and whether they are open if you change the M, instead of M being R, if M is actually this other interval here. Okay, so, and then you have another question here that I will really try to go and answer this thing. If you are struggling with this, you cannot answer, and the thing, you will probably struggle once we are, we start moving towards manifold section and these things. So it's very important. Okay, so I mean, the takeaway is that whether or not a subset is really open depends on your metric, on your pick of metric. So if you have the same set, you might have a metric that generate a completely different open sets. Okay, so as a subset of the same set, under one metric it might be open, but under another metric it might not be open. Okay. So we will actually come up to a question related to this, the notion of equivalent metrics. When do two metrics generate the same open sets. Okay. Okay, so I don't see any question. Okay, so Amir is asking, can you break this down a bit further? You are saying that it is open if an open ball can exist. Yeah. Can we, okay, so Barry is also asking, can we explore? Yeah. Yeah, so this is the same. So the Euclidean metric, so I'm assuming the same, the Euclidean metric in R, which is essentially the standard, modulus, absolute value, A minus B stuff, just this thing here, right? In R, in this case, I'm obviously this is definition in Rn, but this example here, I'm obviously considering just giving you the challenge in R. Yeah. So this is just to see that if you change the underlying metrics, the environment, the sets, the subsets might not be open. Okay. So in this case here, I can actually say this is not open if the thing, whereas this one, the same intervals are open. Okay, so Amir was asking another question. Yeah, so I'm asking whether it's true. Yeah, I think I've already hinted that it's a thing. So it's a challenge.
There is one more question in the question and answer section, which I think
okay,
is good.
I thought so. Okay, so the question Bob is asking, this is a very interesting question. Is the use of open the same as the term open used in topology? Well, we will see that actually. So, but you're already thinking in the right direction, I can say that. Yeah. Yeah, yeah, so okay, so let's go. Was there another question with Amir? Is that the question that I just answered on the chat?
So Amir asked, is this mostly about bounding the metric space?
What bounding in what sense is he asking? Because we need to.
I guess probably the limits of the set.
Yes, yeah. Actually, one of the things that I'll see. I don't think in this session we will cover limits and these things. All this stuff, boundedness of subsets and these things. But in the next session, maybe we might cover that actually to see how you recover those notions from a topological point of view. Yes, yes. Yes, so Schipul circle, yes, that's a good question. Boundedness, this is a property of metric, whereas the other ones are, openness, closeness. These are topological properties. That's a very interesting point he just made. You will actually see, actually in the next session already, I will define what topological properties are, and then as I introduce them, we'll actually in the case of metric, you'll see some properties are metric space properties. The metric property does not necessarily means like it's a topological property. Okay, so. Okay, so Amir is asking, what is the significance of defining openness for metric? You will see, I claim you will see that in the next few slides. Yeah. Remind me, come back to it again if you don't see, you don't get your answer. And then we have Dimitri. We have not established that metric open is the same as topology. Yes, so this is also the same with Amir, Dimitri. As we go along, you will see there is a proposition that will show you this, actually. Okay, so let's just proceed for the time being. We'll come back to the thing. Very good, good points. Okay, so this is the notion of open sets in the metric space sense. Okay, obviously we are trying to build relationships so that the same concept will coincide in a thing with the topological concept that you already gone through. And I claim you will find that in a minute, in a few slides. And there you go. So here's a proposition. So giving any metric space, the claim is that this is true. The first one is the empty set and M are open in respect to the metric D. And also, if you have any finite collection of open sets, their intersection is open in respect to D. Likewise, if you have any collection indexed by any set, this could be, any set really, then this could be infinite, even countable and their union is also open in respect to D. Okay, so the question is, based on what Dimitri and Amir were saying, can you see now the relationship in the thing? Does this give you any deja vu in respect to the stuff that you already covered in the topology session? If not, don't worry. We'll come back to it. You're already starting to see these. I claim this is already familiar to you. You can see this. These are indeed the properties of topology, right? I will make it more explicit in the next few slides. In the next slide, more explicit on actual construction. Okay, and the same likewise the notion of neighborhood. I claim that this notion, I hope I didn't make any typo, is also coincide with the notion of neighborhood that we defined before in the abstract in the point set topology. Okay, now the same way. We had open sets. I also claim, a thing on a metric space, I hope I didn't make any typo here also. A subset is closed if the complement is open, right? Okay, and I have this challenge here for you, whether this is true that these subsets, if M is equals to R, if M is the reals and D is the Euclidean metric, if these intervals are closed. And again, here are some properties. This will probably resemble you the properties of closed sets that we went through. Okay, and finally, part B, you will see